Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and today we're going to talk about impedance. We will start with an overview of what impedance is, and then talk about the frequency dependence of different circuit elements. We will talk about the frequency response of various circuits, and talk about the process of filtering different frequencies. Every device can have an IV characteristic associated with it. Often we will use the Laplace transform to represent these IV characteristics in terms of the impedance. You would have had Laplace transforms in your other engineering classes or in your math class. From there, we can talk about the frequency response of a particular circuit, and we will typically use Laplace transforms to do this. Filters can be written in terms of the Laplace transform, and we can also have circuits that provide a filtering response. Let's talk about current voltage relationships. We already know that the voltage across a resistor is equal to the current through the resistor times the resistance. That's V is equal to IR. We call that Ohm's law. You also know from physics, and we mentioned this at the beginning of the class, that for a capacitor, the current through the capacitor is equal to C times dV dt, where V of t is the voltage across the capacitor. We also know that for an inductor, the voltage across the inductor is equal to the inductance L times di dt, where I of t is the current through that same inductor. Both capacitors and inductors store and release energy from and into the circuit over a period of time t. Ohm's law, of course, remains unchanged. For a resistor, we still have V of t is equal to R times I of t. Remember that a resistor can only consume energy. It cannot store it, nor can it release it. And so V is equal to IR, we wrote as the DC case where there was no dependence on time. But if we look at the Ohm's law in terms of time, we still see that there is very little dependence on time in terms of the relationship, only that the voltage will be proportional to the current. So if we use Laplace transforms, it's a little bit easier to write this information. We can derive the resistance. We call it the complex resistance or the impedance. And so we can write that I of S, where S is the Laplace transform S, I of S is equal to C times S times V of S. So if we write the ratio of V of S to I of S, we see that V of S over I of S is equal to 1 over SC. And we define that as the impedance Z of a capacitor C. We can also write V of S is equal to L times S times I of S for an inductor. So if we take again V of S over I of S, we see that that is equal to S times L, which we define to be the inductance of the inductor L. Let's consider an example. Here's a circuit with one independent voltage source, V of t, which varies with time. We've also started using lowercase letters to represent those voltages and currents that vary with time. So we have a voltage source, a resistor, an inductor, and a capacitor all in series. We can use Kirchhoff's voltage law to write an equation going around the loop. We get minus V plus R times I plus SL times I plus 1 over SC times I is equal to 0, where S is the Laplace transform S. So the Ohm's law, V is equal to IR, is shown in the term for the resistor. We have similar relationships that we previously derived for the current times the inductance times S, that's generalized Ohm's law for an inductor, and 1 over SC times I is equal to V for a capacitor. So we have now generalized Ohm's law to other circuit elements. Okay, Ohm's law applies to the resistor R, but we have a generalized Ohm's law for L and C. We can solve this equation for V, and we get V is equal to I times the quantity R plus SL plus 1 over SC. We can consider the output to be I of t and the input to be V of t. If we make this the relationship assumption, we can now write the gain, which we define to be I over V, the output over the input, as H sub y of S is equal to 1 over the quantity R plus SL plus 1 over SC. If we multiply the top and the bottom of that fraction by SC, we arrive with SC over S times CR plus 1 plus S squared LC, which gives us the relationship by rearranging terms of SC over S squared LC plus SCR plus 1. Now that we have a relationship for the gain, we can talk about the frequency response of a circuit. All we need to do is plug in j omega for the Laplace transform S, where remember j is equal to the square root of minus 1 and omega is going to be the radian frequency. So in our example, we can plug in j omega for S and we get j omega c over 1 minus omega squared LC plus omega, j omega RC. Now, omega is the radian frequency, and we can now talk about other aspects of frequency which you may have used in your other classes. We can talk about the natural frequency omega n, and that's the square root of 1 over LC, and the damping is tau, which is equal to RC. Now, we can take the transfer function and look at only the denominator of that transfer function. If we find the roots of that transfer function, those are going to be the poles of our system. So the denominator for our example was S squared LC plus SCR plus 1 is equal to 0. Using the quadratic equations, we can solve for the two poles. The zeros of the system are going to be the roots of the numerator of the transfer function. So for our example, the numerator was SC, set it equal to 0 and solve for S, and we find S is equal to 0. And that means that we have one pole at 0. There is a special case. For a circuit with no resistance in it, it will resonate forever. Now, practical circuits do have resistance, but you can have circuits with very low resistance. So if we consider our case in our example, but let R equal to 0, then we have poles at plus or minus J over 1 over the square root of LC, which is going to be at the natural frequency. This means that the circuit resonates at that frequency, and the capacitor and the inductor will alternately charge and discharge each other. We could take these poles and zeros and plot them. And when we look at this using MATLAB for some specific values, so we have C is equal to 50 microfarads, L is equal to 20 millihenries, and R is equal to 0 ohms on the left. We have a pole zero map where for R is equal to 0, the poles are actually going to be on the j omega axis. So this means that energizing the circuit will result in an infinite sine wave oscillation of the voltage and the current in this circuit that we use for our example. If we change the value of R to let it equal to 0.01 ohms, which is still a very small quantity, the poles will move to the left of the j omega axis, and we'll see that they damp the circuit by R over 2L, which is 0.25. We can use MATLAB to graph the frequency response using the MATLAB command freq_s, and that will, if we plug in R is equal to 0.01 ohms, again a very small value, we observe the following frequency response. The magnitude is given on the top plot and the phase is given on the bottom plot. Now notice a couple of things. The magnitude is a log-log plot, okay, and the phase is a semi-log plot. Since both the frequency and the magnitude ranges are very large, using a log-log plot makes sense. This is very characteristic of electrical and electronic circuits and systems where both the frequency and the magnitude range may vary by 9 or 10 orders of magnitude, or even more. We can talk about the peak magnitude, where on our graph we can see that peak magnitude occurs where omega is equal to 1,000 radians per second, which is exactly the natural frequency square root of 1 over LC. We call this peak the resonant peak. We can define the quality of the circuit Q to be the ratio of the peak magnitude to the width of the resonant peak. The width of that resonant peak is called the circuit bandwidth. Now let's talk about filters. Filters are circuits that we design to discriminate different voltages and currents based on their frequency. Electrical and computer engineering systems typically have frequent selectivity as a characteristic that is inherent in those systems. We are not typically interested in the static response of any circuit, except in the bias of electronic circuits where the transistor elements must be in the correct state to function in the filtering operation. The other exception is small DC circuits. We can talk about the bandwidth of the filter. That is going to be the range of positive frequencies for which the filter gain is greater than 1 over the square root of 2, which is equal to approximately 0.707. This is how bandwidth is defined. Why this particular value? Well, the power is directly proportional to the square of the gain, since the gain is a voltage or a current gain. So remember we had P is equal to I squared R, or P is equal to V squared over R. So that's a square relationship. If we take 1 over the square root of 2 and square it, we get 1/2. We call that the half power bandwidth. Bandwidth is a fungible unit, and we use it pretty loosely. This is a classical definition rather than a definitive definition. You should always make sure that your understanding of bandwidth is the same as those around you in any practical situation. Decibels, also called dB. So typically, ECE uses magnitude units to be decibels. Okay, it's 1/10 of a bell. This is not a unit at all, but rather the log of a power ratio. So we can define decibels to be equal to 10 times the log base 10 of the power of the circuit divided by a normalizing or reference power. Typically, we use the magnitude and gain of the circuit rather than the power. Since the power is related to the gain by a square, so power is proportional to gain squared, then the log base 10 of the gain squared is going to be 2 times the log base 10 of G. Based on this, we can assume our normalizing power is 1 and define decibels to be equal to 20 log base 10 of G. So be careful to notice whether you're using gain, in which case the decibels will be 20 log base 10 of G, or if you're using power, in which case decibels will be 10 log base 10 of G. This is only because of the definition of decibels in terms of the power. Notice that 20 log base 10 of 1 over the square root of 2 is equal to -3. That's the half power bandwidth, and it's also called sometimes the 3 dB bandwidth. In common usage, we have 4 kinds of filters that are very, very useful. These traditional filter types are low-pass filters, which pass the low-frequency content from the input source to the output, high-pass filters, which pass only the high frequency content from the input source to the output, bandpass filters, which pass a range of frequencies from the input source to the output, and band stop filters, which only block a range of frequencies from the input source to the output. Pictures make this a little bit easier to understand. Here are the ideal filters shown as graphs. Notice that we show negative frequencies as well as positive frequencies. This is typical in electrical and computer engineering. So each of these graphs plots the magnitude of the low-pass filter with respect to omega. These are ideal filters so that we see a very sharp cutoff and it looks quite square. Low-pass filters pass frequencies between 0 and the bandwidth, B. High-pass filters pass, meaning the magnitude's 1 and otherwise it's 0, for frequencies above that bandwidth, B. Band pass filters pass content between B1 and B2, and band stop filters stop the content between B1 and B2. So you can see that the magnitude of the circuit response depends on omega, and we can design it to be one of these 4 different types. In summary, we now have defined impedance. We know that impedance can vary with frequency, and we know that we can plot various circuit values, say VFT or IFT, against frequency, and we call these plots the frequency response. We have also introduced the idea of ideal filters, which can selectively pass and block certain frequencies from appearing at the output.